everybody. Hello, subscriber. We are very happy. We are reaching or we are arriving at the middle point of this course. I would like to remember that every one of the courses included in our academy are composed of 10 lessons. We are approaching the lesson 5, so we are very happy. Well, the name of this lesson is Volumetric Flow and System Head. In the past lesson, in lesson 3, we analyzed the Bernoulli's equation. Remember that this equation was defined for some simplifications, but the most important of them was that the flow was frictionless, non-viscous flow, ideal flow. In this lesson, we will add a point that will get us to closer to reality, to real flow. This approach is the introduction of the pressure losses, the energy losses. So let's go into this lesson. Volumetric and mass flow. Let's recall these concepts. We have defined, or we will define, a flow velocity inside that, or inside a pipe. A is the cross-section area, and rho is fluid density. How is defined the volumetric flow Q? Is equal to the multiplication of velocity by the area. This is the way in which we calculate the flow rate, or the flow, or the volumetric flow Q. Dimensions are volume divided by time. In fact, if we would like to measure the flow rate or the flow pumped by a pump, for example, in a lab, what we should do is to have a calibrated tank, and we should measure the level of water or of liquid in this tank, calculating the volume and measure the time. If we divide this volume by the time, we obtain the flow rate. This is the way normally used in laboratories to calibrate other flow measurement instruments like orifice plates, venturi nozzle, doing or providing a volumetric measurement the way I explained before. And mass flow, F, is equal to the multiplication of density by, between brackets, velocity multiplied by area. Of course, the units of mass flow are kilogram per second, unit of mass divided by time. Since the multiplication of velocity by area is the volumetric flow Q, we can calculate the mass flow as the product of density by the flow rate Q. Regarding the mass conservation law, let's define a control volume between cross-section areas 1 and 2. Here you have formulas to determine the area based on diameter, and we have in every one of these sections a velocity V1 or corresponding velocity 2 for section 2. Let's remember, and I insist, we will use this forever. Let's consider that this is a one-dimensional flow, so the property change only in one direction. This is an uniform flow, so we have mean values of parameters in every one of these sections. This is a steady flow, so the flow doesn't change in time. And of course, there is no leakage between the section 1 and the section 2. So, the mass conservation law can be expressed as indicated in this equation as the multiplication of density by velocity by area, the mass flow rate in every one of the sections is constant. Please note that here we have the density at point 1 and the density at point 2 that could be different. This is the case, for example, of gases. We are talking of, for example, compressed air with a relative low value of Mach number, or we can be talking about sonic flow with Mach equal 1 or supersonic flow. In any case, when compressibility effects are present, we should use this equation, considering density. But what happens for liquids? We can consider liquids as incompressible fluids, so density at point 1 and density at or section 1 and density at section 2 will be the same. So, for liquids, can guarantee the conservation of mass by conserving only the volume. For the same simplification stated before, considering an incompressible fluid, density is constant, the flow rate is constant at every cross section. This is the equation we will use always for liquids. That is our intention here, to focus our attention in those equations that are closely related to liquids, closely related to pumps. The Bernoulli's equation we have seen in the previous lesson was defined for frictionless flow. For a fluid moving within confined walls, maybe a duct or a pipe, elevated at a certain height from the reference plane, we defined in the previous lesson the Bernoulli's equation expressed as energy per unit of volume in units of pressure. Remember that. But now we will express the terms of the Bernoulli's equation as energy per unit of weight. We have divided the previous equation by the multiplication of density by gravity. So the terms of this equation are expressed as heights. That means that these terms are expressed as energy per unit of weight. Being F dimension force and L dimension length, what we have is this. The head H expressed as energy per unit of weight is F multiplied by L divided by F. The result is L, dimension length, a height in this case. Along our professional practice, we will use mainly these two equations when dealing with pumps. For example, we will use this equation expressed as energy per unit of volume when calculating, for example, pressure losses that are normally calculated in the most of the program for calculating losses in terms of pressure rather than in terms of head losses. Another important thing, for example, for positive displacement pump, we will see later when time comes that normally the performance curves of these kinds of pumps are normally expressed in terms of pressure rather than in terms of heads. That is the case of the equation expressed as energy per unit of weight, in which we will be talking about head because the cubes, the performance cubes, for example, rotor dynamic pumps, centrifugal pumps, are expressed as heights. So keep in mind these two equations. We will use both in practice. Let's get closer to reality by adding a new term. We will consider that flow now is not ideal. We will consider viscous flow. Losses, energy losses will be present. The same we have seen before, a confined flow between walls, a duct or a pipe, a reference plane about which we are measuring the height Z1 and Z2. What another type of energy we have in section 2, the energy due to pressure. In green here you see. And the same in section 2. P2 divided by density multiplied by gravity acceleration. What is represented now is the piezometric line. This piezometric line represents the energy line due to hydrostatic pressure at every cross section. What is the another kind of energy that we need to add to the section 1 to obtain the total energy of this section? The kinetic energy. So the total energy at section 1 is the sum of the kinetic energy, the pressure energy, and the geodetic energy. And what happens at section 2? For ideal flows, no losses, no pressure losses, no energy losses, what would be the energy at section 2? If we don't have losses, energy losses, the same level as in section 1. This would be the ideal energy line. But do you think that we will follow this ideal energy line for real flows? Of course not, because we have energy losses, we have pressure losses. So let's represent the kinetic energy at section 2. That will be higher, of course, than kinetic energy at section 1 because we have reduced diameter at section 2, and considering the mass conservation equation, if we reduce diameter, so velocity increases. So we will have a higher level of kinetic energy at section 2, but we will not reach the ideal energy line. There is a blank space here. And what we have on this, the energy losses. Representing in form of the equation what we have seen graphically, we have that total head at section 2 is equal to the total head at section 1 minus the pressure losses. Being the total head at section 2 the sum of the energy or the pressure head plus the geodetic head plus the velocity head is equal to the total energy at section 1 minus the pressure losses. Let's pay attention to one thing I would like to remark. In this equation, we have a part of the energy that doesn't change with the flow rate or with the flow, and another part that does change. The static component of the energy or of the head is the sum of the pressure head plus the geodetic head, as you can see in this equation. So this is the part of the energy or the part of the head that doesn't change with the flow rate, that doesn't change with the flow. And the other part is dynamic head, that this part of the head does change with the flow. Normally the dynamic head is measured, or dynamic pressure is measured with the pitot tube, but we will not enter in details in this course of this kind of pressure measurement. Well, we have came to the end of this full lesson. Summarizing what we have done in this lesson is taking as the starting point the Bernoulli's equation. We have added another term to this equation, considering the energy losses, the pressure losses due to friction. In this lesson, we will add another term to the energy equation, to this equation we are seeing now, because we have considered that there is no energy exchange with the system. No energy is added to the system, no energy is taken from the system. mainly due to energy added by pumps, we will consider this new term in the equation, and we will be closer to the reality. So that's all for today. I'll be waiting for you in the next lesson. Goodbye.